Happy New Year to all our listeners and to my special co-host. 2025 is finally here, and I'm excited.
Yes.
With that, we welcome you to another episode of AI Talks with Chris and Nita.
Absolutely.
Today, we're taking a deep dive into the world of reinforcement learning, or RL.
Right.
Now, you might be thinking, is this about robots taking over the world? Well, not quite.
Not quite.
But it is about teaching machines to learn like we do.
It's more like giving machines the tools to make decisions,
Okay.
but without handing them a step-by-step manual.
Uh-huh.
Think of it like teaching a dog a new trick.
Okay.
You don't write down a code for fetch.
Right.
You reward the dog when they do something right.
Okay. I'm starting to get the picture.
Mm-hmm.
So instead of programming every single rule, we're letting the machine figure things out through trial and error and a system of rewards.
Precisely.
Okay.
Remember when Google's AlphaGo beat a world champion Go player a few years back?
Uh-huh.
That was a watershed moment for RL.
Yeah.
Go is a game of incredible complexity. Yeah.
With more possible board positions than atoms in the universe.
Wow.
Even expert Go players rely on intuition and pattern recognition,
I see.
not just rigid rules.
Uh-huh.
AlphaGo, powered by RL, actually came up with moves that surprised even the masters, moves that weren't in any playbook.
That's fascinating. So it's not just about winning, it's about learning to play in a way that's creative and strategic.
Exactly.
That brings us to the question, how is this different from other types of machine learning that we've talked about in the past?
You're right.
Okay.
There are fundamental differences between RL and other approaches like supervised and unsupervised learning.
Right.
In supervised learning, we're giving the machine labeled data.
Yeah.
It's like showing it flashcards with pictures and words.
Uh-huh.
The machine learns to match the two.
Right.
In unsupervised learning, it's more about finding hidden patterns in unlabeled data,
Okay.
like grouping similar customers together based on their shopping habits.
Got it.
But with RL, we're not giving the machine the answers or asking it to find patterns in existing data.
Right.
We're essentially throwing it into the deep end and saying, figure it out.
Exactly.
Right.
And that figuring it out part is where the real magic of RL happens.
Okay.
Let me give you an example.
Sure.
Imagine we have a robot and we want it to learn how to navigate a maze.
Ah, the classic maze problem.
Yeah.
So how do we apply RL here?
Think of it like this.
Okay.
Our robot, which is our agent in RL terms, is dropped into the maze, which is the environment.
Okay.
Now, the agent can take various actions like moving forward, left or right. Each action leads to a new state,
Okay.
a different position in the maze.
Got it.
The goal is to reach the end of the maze, and for that, the agent receives a reward each time it gets closer to the exit,
Uh-huh.
and a penalty for hitting a wall.
So it's like a video game where the robot is racking up points by making the right moves.
That's a good analogy.
Yeah.
The robot isn't given a map or explicit instructions. It simply learns through trial and error, maximizing its cumulative reward over time.
I see.
Interestingly, defining the reward is often the trickiest part in real-world RL applications.
Oh.
Sometimes the goals are complex, and figuring out what action should be rewarded can be a challenge.
That makes sense. So in this maze scenario, our robot, the agent, is learning by doing.
Yeah.
It's trying different actions, seeing what works, and adjusting its strategy based on the rewards or penalties it receives.
Exactly.
Now, you mentioned different types of RL algorithms.
Yeah.
Could you break those down for us?
Sure. At a high level, we have two main categories, model-based and model-free RL.
Okay.
In model-based RL, think of it as the agent building a virtual map of the maze.
Okay.
It tries to understand the environment, how actions lead to different states, and what rewards are associated with each action in a given state.
So it's like the agent is creating a mental model of the maze and planning its moves based on that model.
That's right.
Got it.
This allows the agent to be more deliberate, like planning a route on a map.
Makes sense.
However, in model-free RL, the agent doesn't bother with a model.
Okay.
It learns directly from experience. It's more reactive, constantly adjusting its strategy on the fly based on the rewards it's getting.
So if model-based RL is like planning a trip with a map,
Yes.
then model-free is like exploring a new city by just wandering around and seeing what you discover.
That's a great way to put it.
Yeah.
Yeah.
That brings up a question. When would you choose one approach over the other?
That's a great question.
Okay.
Model-based RL can be more efficient if you have a well-defined environment, but it can struggle in complex or unpredictable situations.
I see.
Imagine our maze constantly changing its layout. Building an accurate model would be very difficult.
Okay.
That's where model-free RL shines.
Gotcha.
It's more adaptable to dynamic environments.
So self-driving cars, for example, would be more suited to model-free RL.
Exactly.
After all, the real world is full of unpredictable things like traffic, weather, and other drivers.
Right. A self-driving car needs to react to a constantly changing environment. Model-free RL allows the car to learn from experience, constantly adjusting its policy, its strategy for navigating the world.
Okay, you mentioned policy a couple of times now. Let's dig into that a bit. What exactly is a policy in RL?
In essence, the policy is the brain of our agent. It's a set of rules, or more accurately, a function that maps the agent's current state to the best action to take. For our robot in the maze, the policy might say something like, if you see a wall in front of you, turn left.
Okay.
The goal of RL is to find the optimal policy, the one that leads to the most rewards over time.
So it's like the policy is constantly evolving, learning from each experience.
Precisely. And that evolution is guided by something called the value function.
Okay.
The value function assigns a score to each state, representing the expected cumulative reward the agent can get from that state onwards.
Okay.
Think of it like this. States that are closer to the goal in our maze have a higher value because they're more likely to lead to the big reward reaching the exit.
I see. So the agent is not just reacting to its immediate surroundings, it's also considering the long-term consequences of its actions.
Right.
It's trying to figure out which actions will lead to states with higher value states that are more likely to result in getting that final reward.
That's a great way to put it. The value function is like a roadmap guiding the agent towards the most promising paths.
Okay.
Now, you might be wondering how this all ties back to the different types of RL algorithms we talked about earlier.
I was just about to ask that. Does the type of algorithm, model-based or model-free, influence how the policy and value function are learned?
Absolutely. In model-based RL, where the agent is building that virtual map, the policy can be more deliberate.
Okay.
It can use its model of the environment to simulate different actions and their outcomes, essentially planning ahead. The value function in this case helps to evaluate those simulated plans, guiding the agent towards the best one.
So it's a bit like playing chess, where you think several moves ahead before making a decision.
Exactly. But in model-free RL, where the agent is learning directly from experience, the policy and value function are updated more dynamically.
Okay.
They're constantly being refined based on the feedback the agent receives from the environment.
This distinction between model-based and model-free RL is fascinating.
Yeah.
It's like two different learning styles, each with its strengths and weaknesses, but both ultimately aim to achieve the same goal: teaching a machine how to learn and make decisions effectively.
You've hit the nail on the head. And the applications of this learning ability are incredibly diverse. We've already talked about self-driving cars, but RL is also being used in everything from robots learning to perform complex tasks to personalized recommendations on platforms like Netflix and Spotify.
Don't forget about resource management. I read about how RL is being used to optimize energy consumption in data centers, which is becoming increasingly important as our reliance on cloud computing grows.
That's right. And even in finance, RL is being explored for things like algorithmic trading and a portfolio optimization. It's really remarkable how this one technique is finding applications in so many different fields.
It really speaks to the power of RL as a general-purpose learning tool. But I'm curious, what are some of the limitations or challenges researchers are still grappling with in RL?
Well, one challenge is the curse of dimensionality. As the complexity of the environment grows, imagine our maze becoming much larger with multiple levels and moving obstacles. The number of possible states explodes.
Right.
This makes it harder for the agent to learn an effective policy because it has to explore a much larger space of possibilities.
So it's a bit like trying to find a needle in a haystack that keeps growing.
Exactly. And that brings us to another challenge: the need for a lot of data.
Okay.
RL agents often need to interact with the environment for a long time to learn effectively. Think about our robot in the maze. It might take thousands of attempts with lots of bumps and wrong turns before it figures out the optimal path. This can be a bottleneck in real-world applications where getting that much data can be time-consuming or expensive.
So while RL holds immense promise, there's still work to be done in overcoming these challenges.
Absolutely. But despite these challenges, the progress in RL over the past few years has been nothing short of remarkable. And I believe we're only just scratching the surface of what this technology can achieve.
That brings us to the most intriguing question. What does the future hold for RL? Where do you see this technology heading in the next few years?
Well, I think the next few years will see RL move beyond mastering games and start tackling some of the really big challenges facing humanity.
You're talking about things like healthcare, climate change.
Exactly. Those are areas where RL has the potential to make a real difference.
Okay.
Imagine RL-powered systems that can analyze vast amounts of medical data
Yeah.
to personalize treatment plans, predict disease outbreaks, or even accelerate drug discovery.
It's like having an AI doctor that can sift through mountains of information and find the best course of action for each individual patient.
That's the idea.
Wow.
And in education, RL could help create truly personalized learning experiences.
Okay.
Imagine systems that adapt to each student's pace, learning style, and strengths, providing customized instruction and feedback.
So instead of a one-size-fits-all approach to education, we could have AI tutors that cater to each student's unique needs.
That's right. And let's not forget about climate change.
Yeah.
RL could play a crucial role in optimizing energy consumption, developing smarter grids, and even accelerating the development of renewable energy sources.
It's like using AI to help us live more sustainably and reduce our impact on the planet.
And here's where it gets really fascinating.
Okay.
We could even use RL to train AI systems that can design even better RL algorithms.
Whoa.
That's meta learning on a whole new level.
So AI designing AI.
Yeah.
It's a bit mind-boggling, but incredibly exciting.
It's like giving AI the tools to bootstrap its own intelligence, to become more efficient and effective at solving problems.
We've covered a lot of ground today.
We have.
From the basic concepts of RL to its potential to reshape industries and even tackle global challenges.
It's clear that RL is a powerful tool with far-reaching implications. But as with any powerful technology, it's important to use it responsibly and ethically.
That's a crucial point. As we develop increasingly sophisticated AI systems, we need to be mindful of the potential consequences and ensure that these advancements benefit all of humanity.
I couldn't agree more. We need to be asking ourselves not just what we can do with RL, but what we should do.
Well said. And I think that's a great note to end on. We've given our listeners a lot to ponder today, from the technical details of RL to its potential to reshape the world.
It's been a pleasure exploring this fascinating field with you and our listeners.
The pleasure was all mine. And to our listeners, thank you for joining us on this deep dive into the world of reinforcement learning. We hope you've gained a new appreciation for this powerful technology and its potential to shape the future.
As we step into 2025, keep an eye on this field because RL is poised to make some big waves.
And who knows, maybe one day we'll be talking about AI systems designed by other AI systems using RL. It's a future full of possibilities, both exciting and challenging.
Until next time, stay curious, keep learning, and let's continue to explore the ever-evolving landscape of artificial intelligence together.
That's a wrap for today's episode of AI Talks with Chris and Nita. We'll see you next time for another deep dive into the world of AI.